Okay, thanks a lot for the opportunity to give this seminar here online. And for the uh, first time, I would like to just mention that this, I mean, most of the new results which will be covered by this talk were published in a joint paper with Károly Csukás, who was my master student, PhD student, and now after returning from postdoc position and having another postdoc here, uh, is a colleague of me, working uh, on various topics. The plan of the talk is recall some of the basic notions which we need to play around and results which are almost 30 years old and influence the thinking of people in big details. What is you know behind the whole is the concept of isolated self-gravitating systems, which is like other useful concepts in physics, is an abstraction. And usually we think that an isolated self-gravitating system may consist of stars and black holes, and it's far away from other such systems, such that we can essentially ignore their influence apart from gravitational radiation. By the 60s, Bondi, Sachs, and Trautmann developed a very powerful technique applying some asymptotic suitable asymptotic coordinates, and the formalism has played and continues to play important role in studying radiative processes in self-gravitating isolated systems. What is the subject of this talk is much more related to the invention of the concept by Roger Penrose in 1963 of the asymptotically simple uh, spacetimes and the use of conformal compactification as a basic techniques and if we look back, so many decades, we can easily admit that, what was introduced by Roger Penrose was really influencing our way of thinking of isolated self-validating systems. I record here a sort of conformally compactified version of the Minkowski spacetime, which I borrowed from one of the papers by Helmut, because it's really showing nicely, the main structure we should think of, and what was introduced by, the asymptotically simple spacetime as a concept. I should mention here, I mean, at this figure, that I'm going to talk about four-dimensional spacetimes, uh, zero cosmological constant, and vacuum Einstein's equations. And this picture should be almost everywhere uh, used in the arguments which are coming up later. So when Roger introduced the conformal compactification and this concept of asymptotic simple spacetimes, he assumed that there exists a smooth manifold with boundary. The boundary is added to the physical space-time manifold, and the smooth Lorentzian metric, which is just conformally scaled metric. The physical metric is conformally scaled, and this conformal factor is a boundary defining function which is vanishing on the boundary, and the gradient is non-zero. But I would like to emphasize here that the degree of smoothness of the involved structures is critical for the concept of asymptotically simple spacetimes. Uh, the hyperboloid initial data formalism or the hyperboloid initial value formulation was first used by Helmut uh, to show that there are actually many asymptotically simple space-time, at least to the future of the hyperbolic initial data surface. When he also used the conformal field equations he came up with. We showed that if the hyperbolic data, which is sufficiently close to the Minkowskian hyperbolic data, and is smooth, then it develops to something admitting a smooth conformal extension containing a regular point Laplace, which also represents the future of time like infinity. What we will deal, this is a sort of demonstration of what should be a hyperbolic initial data surface in Minkowski spacetime, the conformally compactified Minkowski spacetime. We will use this notion of asymptotically hyperbolic vacuum initial data, which consists of a three-manifold Riemannian metric and the symmetric tensor field. Can you see the mouse with which I'm moving now?
Yes, yes.
Okay, so these three things are such that sigma is the interior of a compact manifold with boundary. The boundary is here at the cut of Scri plus and the initial data surface. The trace of this tensor, symmetric tensor K, is assumed to be bounded away from zero at the boundary. And if omega, I mean, the overcase omega is just the correspondent of omega, but I would like to restrict attention in the entire talk to initial data surfaces. So I use, instead of the capital, the lowercase omega. If this is a boundary defining function, then uh, omega squared times the Riemannian metric and omega times the trace phi part of the extrinsic curvature tensor is assumed to extend regularly to the boundary. Actually, to have a physical initial data, we know that we have to solve the constraints, and the constraint equations in the vacuum case, where there is no source or only these two fields are playing role, can be given by these equations. This is familiar for all of you. And there are many interesting properties of these equations, but at the present, for us, the most important one is that it's an underdetermined system, because we have four equations for the 12 variables stored in these two symmetric tensor fields, 3 by 3 matrices in even coordinates. So typically, the constraints equations are solved by using the conformal or elliptic method for the last 8 decades, which goes that somehow we replace the original, three metric and the symmetric tensor field by conformal rescaling to a non-physical metric, which is freely specifiable, and the trace phi part of the tensor field K is also conformally rescaled in a different power. We decompose the unphysical trace phi uh, K tensor, K tilde, in using the conformal killing operator for acting on a vector or a form field, and the trace phi part of it, and using this covector as a vector potential, and using the conformal factor, I mean, if we choose these four scalar quantities stored by these two objects, then we get this, four variables for the four equations, and the rest is freely specifiable, and it is well known that for this choice, the constraints, these constraint equations form a quasi-linear elliptic system. And when you have an elliptic problem and you have some sort of boundary somewhere, you have to solve a boundary value problem with this. There is also an alternative method which came up about 10 years ago, and because we know that, I mean, we are in this, I mean, we would like to consider configurations close to the one depicted by the figure which I borrowed from Helmut. So sigma can be assumed to be foliated by topological two spheres, and then the simplest thing you can do is just apply an ADM type decomposition using this foliation by topological two spheres. This Riemannian metric can be replaced by the lapse, the shift, and the induced metric on the level surfaces, and the extrinsic curvature tensor can be decomposed to have the scalar, vector, and tensorial projection. And it turns out that this tensorial projection is advantageous to decompose into the trace and the trace-free part. But otherwise, it's simple. What I'm going to refer are spin-weighted quantities in terms. I mean, in order to use those, we have to introduce some sort of complex null dyad, which is familiar for all of you who are ever met with the Newman-Penrose formalism. The dyad is chosen such that this combination gives the unit sphere metric on the level surfaces, and contracting with these dyad vectors the free indices here, which we derived from these two fields, we get some sort of quantities which have spin weights. This is still nothing but the lapse. This is the trace of the tensorial projection, and this other quantity, which is lowercase k, is coming from the vectorial projection of the tensor field Kij. These are the, I mean, I put them in red, indicate that these three objects, this is a scalar field, real scalar field, this is a real scalar field, and this is a spin weight one complex quantity reflecting the vectorial nature of this. So they are four, and we have these four quantities choosing. The rest are in black, the freely specifiable ones. What is important for us that for these variables, the constraints equations can be seen to form a parabolic hyperbolic system. And because these are evolutionary equations, we have to use here initial data even for these quantities if we would like to solve the constraints equations. I should have said that you should ask anytime questions. I mean, it would be better to not to lose the audience, but I proceed if is there any by until now? Okay, then I go on and recall that Larsch and Piotr in the middle of 90s came up with very striking results when the log terms become part of the discussions. They proved that even if the free data is such that these tensor fields are regularly extending to the boundary and there are no logarithmic terms in the free data, the general solution of the constraint fields have poly-logarithmic expressions in omega, which is 1 over the distance from the isolated system. And this means that instead of having the constraints in this simple-minded series expansion, they added some sort of uh, logarithmic terms here with different powers and different coefficients. If we assume that these coefficients are zero, then we get back to this series expansion. So the general solution will have poly-logarithmic expression. This was the first striking result. They also showed that in the non-generic cases, there are non-generic cases, if the initial data such that the initial data can be smooth, that's free from logarithmic terms, if these relations which are in these boxes here, I'm not going to explain it, but they are derived from the freely specifiable part of the data. So if these relations hold on the boundary, then there are no log terms. But these are special cases. And just to remind you that why is it, striking to have these log terms here. This is known for most of you, but even if we have just one single omega factor in front of log n, where n is some integer greater than or equal to 1, this combination tends to 0. So this does not influence the asymptotic decay. But when you look at the derivative of such term, it immediately gets inconvenient. I would like to mention here, I mean, most of the time when I'm going to use series in this omega factor, the coefficients will not be indicated to be functionals, but they are functionals on the boundary. So they have angular dependence, if you want, on this topological two-sphere, but usually I will be neglecting this dependence, or I will show you when this is important. So why was this result so disappointing? Because they actually proved that the initial data which we can construct by using the conformal method is generally not regular enough for the use of Friedrich's existence theorems. And Friedrich's aim was to show that there is a flood of asymptotically simple spacetimes which are fitting to the definition which was given by Roger Penrose. And it's also what was coming out from the analysis of Piotr and Lash was that, for instance, the conformal factor, which is subject of the Lichnerovich equation, is C2 but not C3. And then, when the conformal factor is divided by omega, and this is the basic variable in one of the equations in Helmholtz formalism, the covariant derivative of this, it's really inconvenient to have this. It's also known that, and Lars and Piotr emphasize that if the initial data involves log terms, then the development will also contain such terms. And then one can ask, what will happen? I mean, how can then the metric be decomposed into a sufficiently smooth non-physical metric and a smooth conformal factor? What happens with the concept of asymptotically simple spacetimes? What comes later, recently, there was a very important new result by Florian Bayer and Josh Ritchie, published basically 3 years ago. And they assume that there exists smooth global solution to the parabolic hyperbolic form of the constraints on a hyperboloidal initial data surface sigma. So it's in the physical regime. They also assumed that these solutions extend regularly up to order 4 and 3, respectively, to the boundary. The in the variables which constraint variables which I introduced, the lapse and the trace of the tensorial projection, these real scalar fields will assume to be C4 on up, including the boundary. I mean, this zero with this closed interval indicates that the boundary is included. And the vectorial part, which is a spin weight one quantity, was assumed to be 3C. So this is a very strong assumption. And then they used an impressive Fuchsian equation-based argument and showed that the constraint variables extend smoothly up to any arbitrary order of the derivatives are going to be, the same. These are 4 and 3 in the assumption, but they claim that the constraint fields variables extend smoothly to the boundary then. And they claim that then there is no, the solutions are free of logarithmic terms. I was, of course, excited very much because the parabolic hyperbolic form of the constraints was used by them. But, it was very clear from the beginning that this middle assumption is even stronger than the assumptions used by Larsch and Piot in the special solutions where they restricted the freely specifiable part of the data because these conditions restrict the constraint fields. These constraint fields, the to-be solution. So the main question was for us when we started our investigations, whether we can somehow find an argument using certain suitable physical quantities such that this middle condition, this finite regularity of the constraint variables can be derived in some way from the existence of physically adequate quantities, global charges, and the use of the parabolic hyperbolic form of the constraints. And our strategy was basically to show that if we use the Bondi energy and the Bondi angular momentum, and and we assume that the constraint fields satisfy uh, the parabolic hyperbolic form of the constraints, then we should be able to prove this. And what we did is the following. First of all, using these set of variables, uh, I mean, originally I gave the notion of the asymptotically hyperbolic data in terms of this, but you can translate this to the variables we apply in the parabolic hyperbolic form of the constraints, and then get that the constraint variables have to be related, decay in terms of this omega, which is the inverse polar of the distance from the central region, and the freely specifiable part of the data should behave as indicated here. We assume that the free data is such that the quantities which can be, built up from them and fit to this feature, they will regularly extend to the boundary, but this, serious expansion or, will not contain log terms. If they would, then there was no chance to prove, that the solution can be free of log terms. Even if we assume this, the parabolic hyperbolic form of the constraints are developing logarithmic singularities. I would like to emphasize here, I mean, the free data, freely specifiable part of the data is not containing log terms, but if we put this into the parabolic hyperbolic form of the constraints, they have. For this reason, we assumed that the constraint fields, the laps, the trace of the tensorial projection and the vectorial projection, these are given here, they have the most generic poly-logarithmic ex, expansion, which is compatible with this asymptotically hyperboloidal assumption. We would like to get a hyperboloidal initial data for us. And our main result, I just formulate the result now, and then show some of the some part of the argument beyond. So we choose free data such that they satisfy the asymptotically hyperbolic full of conditions, and they are regular and they are free of logarithmic terms. We also assume that the constraint fields are subject to the parabolic hyperbolic form of the constraints. They are solutions to those. In addition, we assume that these fields, when we look at the asymptotic expansion of them, they possess the most generic poly-logarithmic expansion near the boundary, as indicated above, as I told you. Then the corresponding asymptotically hyperbolic initial data set admits well-defined Bondi energy and angular momentum if and only if all the coefficients of the logarithmic terms vanish up to order 4 and 3 for these constraint variables as it was demanded by Florian and Joss. This was the mysterious middle condition, and we claim that if in addition I mean, we have not only this the missing of the logarithmic terms, but somehow the cancellation of this series expansion terms are also happening, which means that the freely specifiable from the freely specifiable part, these two ones are missing, which is not a big loss. I don't like to have this omega to the minus 1 over here, but also we have this kappa 1 vanishing, coming out from this omegas. So how one can really conclude, using the finiteness of the Bondi energy, that something comes out for the constraint variables. The Bondi energy can be given as the rho tends to infinity limit of the Hawking energy, which is given by this familiar formula. Here one should replace the product of the null expansions into the future directed null directions, which is orthogonal to the two-sphere, the topological two-sphere, but these can be given in terms of our constraint variables. Here is the trace of the tensorial projection, and here is the lapse to the minus 2 power. The area is coming here, and the volume element is divided. This is the volume element of the unit sphere, and this is the scaling factor here. Using the fact that the area and the square root of d goes like rho to the second power, and k star, which is coming here, is also given by the rho derivative of the logarithm of the square root of rho d. This goes like rho to the minus 1. So these are coming from the free data. I mean, you can determine them immediately. So when we have these conditions, they imply that this integrand here has to behave, have to have this specific asymptotic behavior. And this gives immediately restrictions on K and this N hat. And, when we require that this should be finite in the rho equal the Hawking energy or the Bondi energy, uh, uh, which is the limit, then we get, that some of the logarithmic terms coefficients are zero, and some others are involved in some algebraic relations. Just to have an impression, that these are stronger conditions as usually people use. Here, the area is in front of the whole expression, and here, the psi2 uh, in the Garrow-Chart panels, formalism psi2 is appearing, and the shears are given. So here is a rho square factor, and here comes another one. So this is a very strong restrictions on the very spinor components also. So let's go to the Bondi angular momentum. Of course, I have to skip all of the details here, but there is a construction how to define quasi-local angular momentum, and the details can be found in this paper here. I claim that the Bondi angular momentum will be well-defined finite value if these sort of integrals which are coming here for certain axial vector fields, which also specified here, how many are there, and how to construct all of them on a topological two-sphere. So when we have these sort of integrals, they have to tend to a finite limit as we go to infinity. And since here we still have the volume element has this square root of d, this comes as a very strong factor, immediately kills the logarithmic terms from the vectorial projection, or from the spin rate by one version of it uh, up to order 2. You can say that these are not the relations which were claimed to follow from the from from the statement of the theorem which I showed you. But let me mention that and these are all the quantities which should vanish, and we haven't used yet the parabolic hyperbolic form of the constraints. And when we would like to complete the proof of the former theorem, we get that we have to substitute the updated form of the asymptotic expansion. Updated in the sense that we use all these relations which are coming here and put them together with the asymptotic expansion we used in the theorem, and then uh, look at the parabolic hyperbolic, insert them into the parabolic hyperbolic form of the constraints, and sort the terms with powers of rho and log rho. And then, among other relations which were claimed to follow, we get all of these quantities, the vanishing of these coefficients. What was needed for us, that the lapse and the trace of the extrinsic, the tensor projection of the extrinsic curvature tensor are extending C2 form to the to sky, and the vectorial projection uh, has this property up to order 3. So the above findings suggest that the asymptotic expansion for the constraint variables can be given by by these series expansions, where we have, of course, some residuals here. You know, this W with index named by according to the quantity here. So these residuals are assumed to be C0. I mean, they extend continuously to the boundary. You should notice that there is a omega factor, omega to the 4 factor in front of them, which is at the end of the basically the force order derivatives have these uh, properties. And these residuals have to, I mean, not to have a conflict. They vanish at the boundary, and they are capable, as I showed you that you know the logarithmic terms. When you look at the uh, series expansion, including the logarithmic terms, they vanish. So they are really capable to represent the higher order logarithmic terms, which we still may have in the solution to the parabolic hyperbolic form of the constraints. I would like to mention that, instead of making these constant variables reds, now the coefficients, these are functions on the boundary, the functionals. There are three of them, N4 and N4, K, capital K1 and capital K2. These are somehow distinguished among the other, coefficients in black, because and they are referred to as asymptotic degrees of freedom, because the bold-face quantities here, which are in this series expansion, can be given in terms of these quantities and and uh, and freely specify the part of the data. These have no restrictions at all coming out from the set of the equations. And there are some, the asymptotic degrees of freedom as a concept is getting even more established when we notice that the Bondi energy and the Bondi angular momentum, which can be given by these integral expressions here at infinity, at the boundary now, the integrals are taken. They contain, these asymptotic degrees of freedom or derivatives of those, and derivatives of the black side, nothing but the freely specified part of the delta. Here also, the asymptotic degrees of freedom is coming into play into the boundary angular momentum. I don't want to explain this too much. What is important for us that, when we think about the ADM and the Bondi energy and the Bondi angular momentum, and we look at the integral, one should know that these integrals are taking care only of the monopole part of the integrals here. And the regularity of all of the expressions in these square brackets here contains much more information. So not only the Bondi energy and the Bondi angular momentum are coming into play here, but you know actually there exist infinitely many charges uh, guaranteed by the regularity of the integrants in these uh, expressions. I mean, you can determine by them by multiple expansions. So it may be they may be related to the the supercharges, but it's too early to say anything about that. But I would like to talk about a little bit more is the smoothness of the data. So I claim that using the parabolic hyperbolic form of the constraints and assuming that, from the free data, one of the coefficients in capital A, which is part of the induced metric representation in our notation, and uh, the zero coefficients of the trace feed part of, of the tensorial projection contracted by two of these uh, diode vectors can be given by this very simple uh, expression using the scalar part of the projection of the extrinsic curvature, basically on on that the zeroth order constant variable. It has to be non-zero at scribe, because otherwise the trace of the extrinsic curvature tensor could not be uh, uh, different from separated from zero. So what we use, you know, we use this series expansion, but we have these residuals which represent the higher order logarithmic terms potentially. We put this, series expansion together with these uh, concept, these, restrictions on the free data into the parabolic hyperbolic form of the constraints, and we get this a function type equation for the vector valued variable, this W, built up from the residuals uh, on here, such that we have the first order, omega derivative of this W, which depends on, of course, omega, which is the radial coordinate in some sense, and P is just denoting the dependence now on the two sphere at various locations. We have a foliation by topological two spheres, so this is the angular dependence appearance. Here there is a, you know, there is a very, how to say, singular appearing term, 1 over omega, which omega tends to 0 at sky or at the boundary. And here we have the residuals. They are vanishing, but we have to divide by omega. And we have a, a scalar, a vector valued scalar uh, uh, function, uh, which is explicitly known, because we use the parabolic hyperbolic form of the constraints, we put these quantities, and we just collected, what is remaining for these variables. We already know, what are these, and they are regular. And it turns out that this lengthy but explicitly known vector valued function is such that it moves in each of the indicated arguments. Here also the asymptotic degrees of freedom are coming. They have only dependence on the points of the boundary. And what really important for us, that this function h, capital H, extends regularly to omega equals 0. So this is the point. And also these quantities are 0, so when we put omega here to 0, then all of these quantities are dying. But we have to solve these equations as, instead of the parabolic hyperbolic constraints. Now we have to take care of this, and we assume that the parabolic hyperbolic form of the constraints have smooth solutions on the physical part of the initial data surface. So the issue is really related to the boundary. How the solution of this Fuchsian type equation will behave at the boundary. And it's very straightforward to see that a formal solution can be given by this integral equation. I mean, this is a solution. Of course, here, in this capital H, we have the dependence of V and all of these quantities which I suppressed uh, in this notation. But what is really important for us that uh, W has to have this. I have to satisfy this integral equation. I mean, we could solve instead of this equation. What is interesting that when you look at uh, this S variable, which is in this diagonal matrix in positive powers, and here replacing omega when we look at the integral equation, uh, this complete integrand extend smoothly, regularly to S equals 0. And this is the key, that this integrand extend to 0. This allows us to say to replace this variable uh, by the product of omega times tau. And when we insert this, I mean, use this integral transformation according to this change of variables, then we have an integrand here. Uh, Still, we have omega times tau here for S, but from here uh, we can separate the omega dependence and the tau dependence, and this cancels the diagonal matrix in front of this integral here. And in addition, we have uh, a division by omega. Look at this integral here again. So the integrand is completely regular, uh, even at the tau equal 0 um, value. So the right hand side is regular on the entire half closed and open interval. I should have mentioned that originally uh, these values are allowed for omega, but if this is regular, then the left-hand side also regular at uh, this omega equals 0 value, which means that this term and this term both are regularly extend to omega equals 0. This also implies that the first order omega derivative of W has to be uh, regularly behaving at the boundary. And just uh, this means that uh, we can extend this polar expansion one order more. And what is coming out from the repetition of this sort of argument, by an inductive argument, you can show, using derivatives of this Fuchsian equation, we get other Fuchsian equations. Using those systematically, we can show that up to arbitrary order or up to an order of desire, we can show that the higher order omega derivatives of these residuals are all extending uh, regularly to the boundary, which means that we can show the extension of the constraint variables up to the boundary, up arbitrary order. I already used plenty of time, so I'm going to skip the second formulation of the second uh, statement. The first two conditions are basically the same, and then we show just that the constraint fields are also smooth on the entire uh, uh, initial data surface, including the boundary, that is no logarithmic terms uh, occurs if the uh, occur if the if and only if the well-defined Bondi energy and angular momentum uh, can be associated with the system, and we have these restrictions uh, to on the boundary for the freely specified part of the data. So, as a summary, I would like to say that we proved the existence of well-defined that the existence of well-defined Bondi energy and angular momentum, together with some mild restrictions, much milder than used by uh, Larsch and Piot, or much milder than used by Florian and Jost, uh, uh, guarantees that the generic solution to the parabolic hyperbolic form of the constraints equations are free of logarithmic singularities. I don't want to spend too much time on this generalization issue, but since the Cauchy developments of smooth asymptotically hyperbolic initial data have smooth conformal boundaries, I would like to emphasize that our results are in accordance with the smoothness assumptions used by Penrose when he introduced the concept of asymptotically simple spacetimes. And one more note is, of course, uh, an interesting issue. Is there any way to control the asymptotic charges we have at infinity when we would like to construct the solutions to the parabolic hyperbolic form of the constraints in, say, in a perturbed Kerr black hole, such that our initial data surface cuts the uh, event horizon, or the dynamical uh, horizon, and goes out to sky. But this is in progress. One way to do this is to use somehow the Fuchsian equations, such that one can have some sort of control where Fuchsian equations are involving all the asymptotic degrees of freedom. And I would like to stop here, and thanks for your attention. Sorry for using too much time.